Hey guys, welcome back to another video from Beyond the Five. Today we're going to be reviewing and really just talking about chapter 3.6, which is the deviation from the ideal gas law. So the enduring understanding is that gas properties, this is like last week's, is that gas properties are explained macroscopically, using the relationships among pressure, volume, temperature, moles, gas constant, and molecularly by the motion of the gas. So real gases have different properties and behaviors from ideal gases. The ideal gas law is unable to explain the properties of real gases. And so deviations from the ideal gas law may result from interparticle interactions among gas molecules, particularly at conditions that are close to those resulting in condensation. Deviations may also arise from particle volumes, particularly at extremely high pressures. So what postulates actually accurately explain real gases' properties and behaviors? So the first three, like I talked about last week, the first three postulates are accurate, or last video, sorry. The last three postulates are accurate for real gases. The last two, numbers 4 and 5, are inaccurate. So gases actually do have volume. At high pressure, low temperature, and low volume, the volumes of the particles is no longer negligible compared to the volume of the container. So last week for postulate 4, I can go back. Postulate 4, the molecules composing the gas are negligibly small compared to the distances between them. And so the deviation from the ideal gas law says gases actually do have volume. They're no longer negligible. And then the fifth postulate was also wrong. Some gases do actually repel each other. At high pressure, low temperature, and low volume, the attractive or repulsive forces can impact strength of the collisions. So I'm going to go back. And it says gas molecules exert no attractive or repulsive forces on each other on the container walls. Therefore, their collisions are elastic. But in reality, with real gases, some gases do actually repel each other. And so this chapter is pretty short, but this question is from Sean Bryan at the College Board. And it says, explain the following statements about gases. Be sure to mention specific information about both gases. So argon deviates more from ideal behavior at extremely high pressures than neon does. So this is because argon atoms have a larger radius than neon. At high pressure, low volume, the volume of the atoms is no longer negligible. The volume that is actually occupied by the gas is less than predicted by the ideal gas law because so much is taken up by the atoms. When volume is decreased, the observed pressure is actually greater than predicted. And so this is going back to that fourth postulate. Gases actually do have volume. The volume of the particles is no longer negligible. And you can see because argon atoms have a larger radius than neon, the volume of the atoms is no longer negligible. And then this is the second question. The pressure of sample CH4, which is methane, is closer to the pressure predicted by the ideal gas law than a sample NH3, which is ammonia. And so this is because methane, right here, is a non-polar molecule, while ammonia is a polar molecule. So just like from chapter 3.1, we know a non-polar molecule, all the bond dipoles cancel each other out, but for a polar molecule, they don't. And so therefore, there are much stronger IMFs present in a sample of ammonia than in a sample of methane. And we know that from the polar and non-polar properties. And so the IMFs cause molecules to be more attracted to each other, causing fewer collisions with the size of the container. Actual pressure of ammonia is less than predicted pressure. So because they're not bouncing off the walls that much, which would cause higher pressure, they don't have as much pressure. And then they're instead attracted to each other. And normally the kinetic molecular theory would say, no, they don't actually exert any forces on each other. But in reality, some gases do actually repel each other
and the attractive or repulsive forces can impact strength of the collisions, and then the pressure. And so again, like last week, if you found this unit or this chapter particularly confusing, I really recommend that you watch the video from the College Board. It's a really great video, it's a great review, and if you didn't understand something, it's a great resource for you to use. And I'm so grateful for the College Board and what they've done for students this year. So here's our bibliography for today, and I will see you guys in the next one. Thanks for coming today.